So it's 6 p.m. Let's wait for some time. Few people join and they left because I told them that I will start after 6. So let's wait for some time so that people can join. Otherwise, I will start after a few minutes. Okay, so let's start the session. I think people can join in the between also. So hello everyone, welcome to the live session for the course Sensors and Actuators. So this is week 12. So this is our last live sessions. We have already covered a lot of the topics that has been discussed during the course, lecture videos and lab classes. So if you are attending the live session for the first time and you don't know me, then let me introduce myself first. I am Ananya. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. I conduct the session every Tuesday for this course Sensors and Actuators between 6 to 8 p.m. So the main purpose for the live sessions in NPTEL courses is that to solve some problems, those are related to the topics, those are covered during the week, as well as those can be helpful to solve the assignments. So most of the time the questions are numerical, but for this course we don't have that many numerical questions, so we mainly focus on small theoretical questions during the live sessions. Along with the questions, I also try to give a brief overview of the topics those were discussed during the class, like in the lecture videos and in the lab classes, so that everybody is in the same page. So ideally you should watch all the lecture videos and lab classes before coming to the live sessions, then it will be more useful. But if you have missed few topics, then maybe I can give you an overview and you can pick up from that. Okay, so let's start the session. So I'm using this picture in picture mode in Google Meet, so maybe you will see a small screen here, but this way I can like interact with you. So I will try not to write here in this part of this presentation. Okay, I will write mostly here. If you can't see, then let me know. Okay, I hope that I'm audible to you. You can see my screen, and the background noise is not disturbing. If you find any disturbance, then please let me know. Okay? So the first topic that was discussed during this week, no means there is no disturbance, right? You can hear me clearly. hope that there is no problem. Okay, so let's start. Okay, thank you. Thank you for the confirmation. So, the topic for this week, for the first topic was biosensors. We have been discussing biosensors in last few weeks, mainly biosensors for breast cancer detection. So this week also we started with this topic, and that biosensor that was discussed in the class, that is to measure different properties, not only one property. So we know that most of the time the sensors are of electrical type. So the sensor output can be of any form. It has to be some readable format. Most of the time the output is electrical, because it is very easy to use an electrical signal in a system, because we don't normally use the sensor itself. We integrate with other circuit elements. For example, we amplify it, we filter the output to get the a good result, good output in a very good form. Okay, so most of the time the output of a sensor is electrical, but there may be other types of output of a sensor, can be mechanical, thermal, optical as well. So the biosensor that was discussed during the class, it can provide multiple output actually, in terms of an electrical signal, in terms of a thermal signal, and in terms of a mechanical signal. Okay, so I will write it down, the different properties. That was measured was electrical, that we can measure using the biosensor, that was discussed particularly during the class. That was to analyze the electrical, thermal and mechanical properties of a tissue that may have breast cancer or may not have. Now we are trying to see whether the tissue is cancerous or not. Okay, so the different properties the sensor can measure: electrical, mechanical and thermal. Okay, now what can be the electrical properties? We know that the tissue will have certain impedance, and the impedance value, so impedance is like resistance, but it has an imaginary component as well. So the impedance may be different for a cancerous tissue and a non-cancerous tissue. We can measure that using a biosensor. And the mechanical property can be the elasticity of the tissue, the stiffness of the tissue, and then the thermal property can be the thermal conductivity of the tissue. Okay, so these are the properties that can be studied, and we have to analyze these signals, the electrical, mechanical and thermal signals and thermal properties, in order to differentiate a cancerous tissue and a non-cancerous tissue. And that is a completely different signal processing part in a biosensor. So we should be able to we should be able to differentiate the cancerous and non-cancerous tissues properly, and that requires extensive study and analysis. Okay, now let's focus here on the fabrication part, because that is what mainly is being discussed during the class. The sensor design can be different depending on the type of the disease that you are trying to determine, or the type of the analyte you are trying to determine. So what is an analyte? Basically whatever the physical thing you want to sense using a sensor, that is what we call as an analyte. Okay, can be biological, can be a chemical also. So whatever property or whatever type of analyte that we are trying to sense, depending on that the sensor design can be different. Depending on our requirement, the sensor design can be different, but more or less we use the similar fabrication process in many of the sensors, because we normally what do in a fabrication, we deposit, we pattern using lithography and etching, and sometimes we do, depending on the material requirement, if we need a doped material, doped semiconductor, say. Okay, so the sensor that was discussed during the class, it has the structure was something like this. You may read Professor Pandya's papers from his group to understand the design more. I'm just giving you an overview. I think that is the work was done by his group, the sensor that he has discussed during the class. So the it has something like this a structure. So we have a silicon suspended structure like this can be done using bulk micromachining. We have already studied what is bulk micromachining and what is surface micromachining. So it is silicon. We remove most portion of the silicon wafer uh, by using bulk micromachining, and we often make the structure to create to make a pressure sensor, so that this suspended structure so this silicon part will bend depending on the pressure applied. Okay, and sometimes to make a cantilever we use surface micromachining. And then we have SiO2 layer. Most of the time we will have a small SiO2 layer on top of silicon, and then many times we grow SiO2 layer for different purposes. For example, it can be used as a mask, right? So there was this SiO2 layer in his design, and then there was this heater to measure basically the thermal properties. So this is the heater. Of course there will be some kind of structure, like we know that the resistance, if we have a coil kind of structure, then this structure will have certain resistance depending on the size of this wire, the length of this wire, and the thickness of the material, and the width. Okay, and the different design will have a different resistance. So the heater design probably they have optimized to achieve a certain temperature. Okay, and after that there was another SiO2 layer. Okay, so this is again SiO2. This SiO2 is an insulating layer, because heater is normally made up of like metal lines. We will apply electric current through this, and because of Joule heating some temperature will arise. I'm so sorry, the connection got lost in the middle, so I hope everything is okay right now. So let me share my screen again. And I will use picture in picture mode again. There was some internet issue from my side. I'm so sorry for that. So let's start again. Okay. So what I was discussing is that the heater, this is made up of some metal. So obviously we will make some pattern like this using metal deposition, and then by using lithography, or we can do the lithography first and then the metal deposition and then etching. Okay, so we have already studied these processes earlier in earlier sessions. So because this is a metal, to make any metallic structure on top of it, we will use an SiO2 insulating layer. It provides great electrical insulation. You should look for the properties of SiO2. So we have discussed earlier also in one of the live sessions. So the properties of SiO2 is such that it is very useful in microfabrication. Okay, so depending on the thickness and the quality of SiO2, we use this layer in different purposes. We use it as a mask oxide, we can use it as a filled oxide. There are different applications of SiO2 in microfabrication. Okay, so after this insulation layer, we will basically have our piezoresistive sensors. Those measures the mechanical properties. So what are the piezoresistive sensors? So piezoresistive sensors are the materials or the sensor that changes the electrical properties, mainly the resistivity of the material when a force is applied. Okay, so we will have the piezoresistive materials. Again, the design will be depending on certain optimization. It will have certain design, and then we will have electrodes for the sensors. Okay, we will apply we'll have electrodes so that we will measure the resistivity. So for that we will have our interdigitated electrodes first. So again, this is not an uniform layer. So this is a pattern electrode, interdigitated electrodes. We know how to make it using photolithography and metal deposition and then etching. Okay, so I have discussed this several times, so I'll not go through it again. So after interdigitated electrodes, we will have our piezoresistive sensors. Okay, so piezoresistive sensors, and this will measure the mechanical properties along with this micro machined silicon wafer. So this wafer, whole wafer will bend, and the force will be like the force will be reflected on the change in resistivity of the sensing layer, piezoresistive sensing layer. And then we will have again another SiO2 layer. So this will be our third SiO2 layer. Okay, this is to make again the insulation, and then we will have our electrodes, one electrode that is to measure the electrical properties of the tissue. Okay, that means the impedance of the tissue. So for that we will have, what we will have gold. So this will be gold, and then there will be SU8 pillar. Again, this layer is not uniform. Okay, I'm just showing you the different layers, and on top of that we will have again gold, so that we can have a metal contact. Okay, so this electrode will measure the electrical properties of the tissue. So we will place the tissue on top of some electrode or some metallic structure. That will be the another part of the electrode, and then this will be the one electrode, and these are the piezoresistive sensors to make study the mechanical properties, and the heater. So we will apply certain heat, and that heat will conduct through the structure, and if we place a tissue here, the heat will be transferred through the tissue, and with the help of a thermocouple, how much heat is being transferred through the tissue, we can measure the thermal properties of the tissue. So this is how this kind of a sensor works. Now this is a very complicated structure, I'm sure the design must require a lot of optimization, and then multiple like set of study, set of like fabrication, and then analysis, all these things, multiple steps to achieve a biosensor that can measure these three properties. So if you are working in the design of a biosensor, so maybe you are already familiar with such kind of process, that we will start with a design probably in some software like COMSOL, and then we will optimize that design, we'll go for fabrication, we'll do the characterization of the sensor. That involves like two types of characterization. First, we will characterize whether our dimensions are correct or not, whether our sensing layer is working properly or not, all these things. And then we will use it to make it like for actual sensing and see whether uh, we are getting desired response from our design or not. There may be some design error, there may be some fabrication error, and we will repeat the process multiple times so that we get the desired response. Okay, so this is how the basic flow of how we can actually design a biosensors. Now, because this particular design we are discussing for breast cancer analysis, Professor Pandya has also discussed about different stages of breast cancer, breast anatomy, all these things. So please let me tell you that I'm not an expert in this area. So I have not worked in like breast cancer detection using like some sensors. Okay, so I'm just giving I will just give you a few notes for your reference so that you can remember it for the exam, and like overall if you are working in this area, basically the things that was discussed during the class, different stages of biosensors. Okay, so I'll write it down. So different stages of breast cancer. Few questions in the assignments are based on this, so that is why I'm giving you this. So there are 0 to 4 stages. Okay, this is based on the tumor size, lymph node involvement, and spread area. Okay, so first one is stage 0. So uh, that is when the cancer cells are only at the duct. Okay, and next stage is stage 1. So stage 0 and stage 1 is like curable. The chances that the patient will recover after treatment, if she is in stage 0 and 1, the probability is very high. So we want to detect the cancer during these stages, so that is the main aim. So that in this stage the tumor size is less than or equal to 2 centimeter. That is how it differentiate. And then stage 2, so stage, okay, this is where the tumor size is 2 to 5 centimeter. Okay, and it involves nearby lymph nodes. So these are the nodes that mainly present in like near armpit and all this positions. Okay, maybe you can study more. Okay, and then the next stage is stage 3. So tumor size is greater than 5 centimeter in this case, and also it involves lymph node and significant spread. Okay, and then the last stage is the stage 4, which is known as the metastatic breast cancer. So this is like kind of like the last stage. And here the cancer is spread the distant organs also. It is disturbing other parts of the body as well. Cancer has spread to distant organ. So you can see that like one if you want to work in this area like in biosensors, so that we have to like have the knowledge of biology, how the human body works, as well as microfabrication, the design aspect, different how to run how to different softwares, how to run different softwares, as well as the electrical engineering aspect also if we want to make an electrical sensor. So it involves multiple subjects, and because I'm not working in this area, so I don't have like all the knowledges of the breast cancer or other topics, but overall I can tell you how the microfabrication parts work, because this is where I mostly work. I'm working in my PhD. Okay. So this is for your reference. You can look it. I share the PPTs like each week, so you can look at different stages, and just this is just for you as a quick note. Okay. So the next topic was MEMS based sensor for catheter contact force measurement. So we till now we have discussed about biosensors for breast cancer detection, and here in this topic the Professor Pandya has discussed about how we can use the sensing technology for heart diseases. Okay, so what disease that we have particularly discussed during the lecture? So that was atrial fibrillation. So let me write it down. So what is it? Uh, this is basically when the atria, so this is the upper part of the heart, it beats irregularly and often rapidly. Okay. And this disturbs the normal blood flow, and increases the risk of heart failure. So what is the surgical treatment, medical treatment for this disease? So the treatment is catheter ablation. Okay. So the catheter is like a tube that can travel through the blood vessels, okay, and towards the heart, to the heart. And catheter ablation means burning. Okay. So using this process, using this treatment, the part of the heart, the part of the tissue that is creating, that is responsible for this condition, those part will get burned. Okay. So a catheter, so which is a thin, flexible tube, so that catheter is inserted through blood vessel and to the heart. Okay, uh, it delivers energy. It can be a different type of energy. Just for the time being, I'm saying that it delivers energy and destroys the area that is causing abnormality. Okay, any kind of abnormality, the way that our heart beats, any kind of irregularity, any kind of abnormality that is caused by the area, that part of the tissue will get burned using some kind of energy. And the type of energy can be RF energy, okay, that is known as RF ablation, or cryoablation, so that is like cold energy. Okay, now why we need a contact force measurement for that? So the tissue will have certain kind of mechanical properties, and that we can measure. And it is very important to like ablate the tissue or burn the tissue completely, uh, because otherwise the condition may reoccur. Okay, so that is why we use contact force measurement or force sensors, so that first it will try to sense the tissue and then will apply appropriate energy so that it gets burned. Okay, so that requires a lot of calibration. So how a normal tissue behaves when the force sensor comes in contact with a normal tissue and a tissue that is causing this kind of heart problems. Okay, that this prior knowledge is required, and after calibrating all these things, we can use this kind of a sensor for for this kind of medical purposes. Okay, remember that anything, any kind of sensing technology we will use in case of medical treatment or for biological screening requires extensive optimization, extensive analysis, because we are targeting something that is very critical. Okay, we have to do this measurement repeatedly and ensures that our data, our result is correct. Okay, so in this case, contact force measurement or a force sensor can help. So how the design was, we will use this catheter say, and we will put the force sensor at all sides of the catheter. Okay, we will put at the all sides. And so I will not go through the design part of it like again, because this was discussed during the class. One thing that I want to discuss here is that so we know that how we can measure the force. We can use a force sensor, right? To use to make a force sensor, we can use a piezo-resistive material. So the property of the material will change when force will be applied. Now, what is a piezo-resistive material? In last class or during this week also, we have studied that P.PSS on PDMS layer can be a flexible force sensor. So P.PSS is a conductive polymer that has piezo-resistive property. Another type of material that is often used, we have discussed earlier also, that is boron doped silicon. So boron doped silicon shows very good piezo-resistive properties, so we often use that. Now how here comes the doping part of microfabrication. As I discussed earlier, during in microfabrication we have this four components. One is this deposition, that is like uniform material deposition, and to make some kind of pattern, some kind of structure, what we use lithography as well as etching to make the patterns. Okay, obviously that also involves deposition. Okay, Now another component is the fourth component is the doping. So when we want to change the material properties, we go for doping. Okay, we know that in silicon, if we dope boron, then it will become a p-type material, and if we doped phosphorus, then it will be n-type material. I'm not sure how many of you are from like ECE background, electronics and communication, where we mostly study solid state physics, solid state devices, where we study these things about semiconductors, about silicon. So probably we like all of you know this, that when we dope silicon, either it will become p-type or n-type, depending on whether it is a pentavalent dopant or an trivalent dopant. Okay, so when we dope boron, in case in silicon, that will give us a p-type material. Okay, now p-type material, so that is that is how the electrical property of the material will change. What other property it will change? The piezoresistive property. Okay, boron doped silicon is often used as a piezoresistive material. Now how we do this doping? So there are these two components, like we do doping in semiconductor or in microfabrication. We do doping using two techniques. One is this diffusion, another is this ion implantation. So I'll not discuss about ion implantation. I briefly I will discuss about voice issue. You cannot hear me properly. Should I speak louder? Am I audible to you now, or there is background noise? So will it be okay if I speak louder? Okay, I'll try to speak louder. Actually, the fan is on. I think there is some background noise because of that. So let me know if you can't hear me again. So I'm trying to speak louder. Okay. So I will not discuss about ion implantation. I will discuss about diffusion, because that was the process was discussed during the class. I will discuss about it very briefly. So you can see here, so this is a silicon wafer, and there is an opening here. Okay, so this might be SiO2 layer, that is like an insulating layer. And then what we do, we expose this wafer in some source of the dopant material. It can be a gaseous source, it can be a liquid source. So if I remember correctly, in the class the source that was used for boron doping was liquid. Okay, so when we expose this in some source of the dopant, then this top part of silicon wafer, so the dopant atoms will come like sit near this top part. Okay, so this white portion you can see, so this is the pre-deposition part. Okay, so initially there will be some deposition, and then what will happen, so we will apply some heat or thermal energy, and this dopant atoms will like travel below to a certain distance, and this process is known as the drive-in process. Okay, so this is how boron doping is done, or any other doping is done in silicon. Okay, so that we get a material with a different properties. So the silicon will have a different properties. We know that in case of electrical properties, the resistivity of the material changes when we do doping, and since we are talking about piezoresistivity due to boron doping, the piezoresistive property of silicon changes. Like the material will have notable piezoresistive property. So for that we use this diffusion process. I just wanted to tell you that so this is one very important part of microfabrication, that we often do doping of our material, because we normally want to change the material properties, and we can do that by using doping. Okay, along with diffusion, lithography and etching. So this is also one important components in any microfabrication process. Okay, so this was about this topic. Let's move on to the next topic. I hope that I'm audible to you properly right now. And the last topic that we are discussing, so we have already discussed earlier also in last week also about 3D printing technology. So I've discussed about 3D printing technology. I will just give you some notes for this, like for your upcoming exam. So what was discussed during the class. So what we learned during these videos, there are 5 types of 3D printing technology, and what are those? I'll write down the name. So first one was fuse deposition modeling. Okay, so the short form is FDM. uh, the second one was stereolithography. SLA, so this is the short form. I will often use this term. Next is selective laser sintering. SLS. Next is laminated object manufacturing. LOM. And last one is material jetting. So we are more familiar with the first one and the last one. So this is like inject printing, and this is like printing using like a plastic wire. Okay, so let me discuss briefly about each of these topics. So first one is FDM. So how it is done, it was discussed, the lab video also discussed about this, that was also on this FDM technology. So we'll have a 3D printer. There will be like a filament that will be of some material, say PLA and ABS. You should look for the full form of PLA and ABS. I also don't remember, but these are like thermoplastic. It gets melt when heated, and there will be one nozzle, and through this nozzle, that thermoplastic wire will come, and then it will get heated, and that will get melted, and using that we will write something. Okay, and how it happens in layer by layer. So we will provide a code to our printer, so that will give like XYZ coordinate, where we will give XYZ coordinate, like where to put the material and where not, and that will create the structure layer by layer. Okay, so this is one very common type of 3D printer. We can make like different structures using it, but the precision, the dimensional accuracy is not that good. But to make simple structure, to make like a covering for something, it is a very good printer. Okay, and many times we can have this in like small labs as well as in home setup also. So it is very easy to set up and learn and make something using this. Okay, so it has a thermoplastic filament which is melted. Okay, next important point here is that it does layer by layer printing. Okay, and how it does with a nozzle. So it has like this kind of a structure, so this is not very good. So the material will come through this nozzle. Okay, So we also have this kind of a machine in our lab. Sometimes suppose we want to make some structure to hold something of certain shape, then we use this 3D printer to make like a support kind of structure. Say I want to place my sample in front of a camera or in front of a laser vertically, so I will make a structure that can support my sample or different sizes of sample in front of it, so that I don't have to hold it by manually. Okay, so if I hold it manually, there may be some tilting or something, so we make this kind of a structure very easily in the lab, okay, using this kind of a system. But the problem is that the accuracy is not that good. And you will see the layers, okay, because it prints layer by layer, so you will see each layer, it is visible, very visible. And the materials, like PLA, ABS, please look for the full form of this materials. Okay, next topic is stereolithography, so SLA. So how it is different? So it uses UV light, UV source, UV laser to cure liquid resin. So you know how the process looks. It was discussed during the class. This is just like a reference note for you. So we will use the laser again, layer by layer, to cure the liquid resin. Okay, and that's how we will create the different structure by layer polymerization of the liquid resin. Okay, so these uses normally like photopolymers. Okay, so the material is uses photopolymers because we are using a UV light to cure, so that is why it is just a photopolymer. Basically the property that changes due to UV laser. Okay, those will become hard upon exposure using a UV laser. And the next is SLS. So what is the difference between SLA and SLS, selective laser sintering? Here we use a laser, okay, and we use, the main difference is that we use here powdered material, not liquid material. We use powdered material here. Now what is sintering? Sintering is like you will have this powder material and you will melt it, but not completely. You will melt it enough, you will provide sufficient energy so that it almost, the powder almost gets melt, like from solid to liquid form, and during that process it kind of combines. Okay, it makes like a solid structure, and then you again will remove the laser source, so it again becomes solid. So again the solidification will happen, and that will create like a block. Okay, that is what sintering means. Okay, we use powdered material here, so that is the main difference with this other techniques. Okay, then the next is, it is not right. Okay, LOM, laminated object manufacturing. So this is also a very like simple and cost effective technique. So what it uses, so it uses layers of sheet material, so it can be paper, plastic type of material, layers of that material, those are laminated and cut into pieces. Okay, again you can see that the accuracy will not be, the dimensional resolution will not be very good because we are cutting it using some laser or something. Okay, so the accuracy will not be that good, but this is also a low cost process to make some kind of structure. Okay, material laminated The materials can be papers, plastic, foils, etc. Okay. Basically anything that you can make a sheet and then cut using laser or something. Okay. And the last technique that is very popular, so many material science people are working in this area, material jetting. Okay, because somehow we are limited with the material choice in other techniques, but in material jetting, so this is very similar to like insect printing, using like a normal ink, but instead of that we will use some material. Okay, as I discussed in earlier sessions also, like if we can suppose we want to make some structure using some material, normally what we do, we deposit it uniformly, then we do lithography and etching to make the structure. Now if we can make like the ink of that material and we can use it for 3D printing if we don't need a very fine features. Okay, obviously using these techniques we cannot make like a nano dimensions features, but somehow if we can make the ink of that material, required material, then we can just use it, then we can just print it using material jetting or like an insect printing, and that will reduce so many steps in lithography and etching and deposition, all these things. Okay, we can directly get the structure, so that ensures rapid prototyping, right? That is what we discussed in earlier session as well. So here what happens in material jetting, droplets of polymer or the material, whatever material we are making, jetted, kind of like spread and then UV cured. Okay. You know what is curing, right? We have discussed about PDMS curing in earlier sessions. You must have watched the lecture videos as well, okay, in the portal. So these are different types of 3D printing technology. Please go through the lab classes how we can use such a system, and this is very versatile. Many people are working in this area with innovative materials so that we can cut different stages in microfabrication with just one step printing. Okay, so these are the topics, those were covered in this week. I will go to the questions next. If you have any question, then you can ask. I'm taking a pause. I'm like shouting. I hope that you can hear me clearly. If there is no question, then let's go to the questions and answers. I will provide you the question and again wait for some time so that you can answer like the earlier sessions. Okay, the first question is, let me write it down first. Why is gold commonly used as a sensing electrode material in biosensors? Okay, I will give you few options. First is it reacts easily with biological samples. Option B is it has poor electrical conductivity? Option C is it is chemically inert and biocompatible. So what is the answer? You already know the answer. Why we use gold electrodes? Now gold is expensive, but we still use gold, say instead of copper or something, as a sensing electrode, mainly in biosensors. So uh, what is the answer, considering it that I am asking it for particularly for biosensors?
Answer C.
Yes, it is chemically inert and biocompatible. So we know that, for example, we use gold jewelry, right? It is chemically stable, right? It is non-toxic. It does not react with the normal chemicals or with our skin or something. Many people are allergic to other materials, but most of the time not gold. Okay, so it is biocompatible. It is not toxic. Also it has good electrical properties to so that we can use it as a sensing electrode. Okay, so these are the advantages of using gold electrodes, especially in biosensors. If we don't want to use it in biosensors, we just need an electrode, we can make an aluminium or copper electrode also. Okay, but for biosensing applications we have to be careful. Okay, so gold is stable, non-toxic, and does not corrode. Okay. These things make it ideal for biosensors. Let's go to the next question. So we have discussed about a biosensor that can measure electrical, thermal and mechanical properties. So the sensor is called ETM biosensor, electrical, thermal and mechanical. So what are the properties? What are the properties particularly? I know that it measures electrical, mechanical and thermal, but what are the properties it particularly measures? Okay, you should be very specific with the answer. So I'll write a question here. What properties are typically measured by an ETM biosensor? So I will not give you options. If you have watched a lecture video, then you will be able to answer. So what is the answer? In electric
Ma'am, it's impedance,
impedance, in electrical it
thermal
measures
conductivity, and stiffness.
stiffness. Yes. So electrical, it measures impedance. It can measure resistivity as well, but we are measuring the impedance with the example that was discussed. Thermal is the conductivity, that is thermal conductivity, not electrical conductivity. We can measure diffusivity of some material also in some other type of say biosensor, but in the particular example we studied about thermal conductivity. And then mechanical, is the stiffness, or it can be the elasticity of the material.
Excuse me, ma'am.
Yes.
Ma'am, resistivity, if we talk about resistivity, then we talked about resistance. If we talked about impedance, that means in that case also we can measure resistivity.
Yes, like if there is no imaginary component in the impedance, then it is resistance. And resistance and resistivity is related. If we know the dimensions of the material, dimensions of the tissue, so resistance is equal to rho L by A. So if we know L and A, then we already know resistivity, right? Sometimes it depends on the configuration as well. For example, you may have studied this 4-probe configuration. Okay, so there will be this 4 probes. 2 probes will be used to like flow a current, and 2 probes is to measure the voltage. Okay, there will be the sample below here. So this configuration measures the resistivity, so it is independent of the thickness uh, and the size mostly. Okay. So 4 probe configuration is used to measure resistivity, and suppose we use 2 probes, then it will be resistance. Okay, now how we are measuring, that will depend, like whether we are measuring a resistivity or a resistance value. And impedance, if we have a complex resistance, impedance is like resistance, then it's impedance, just like that. The difference is in the configuration, whether it is a 2 probe configuration or a 4 probe configuration. Okay? And from 2 probe configuration also, even though we are measuring resistance, if we know the dimensions L and A, then we can figure out the resistivity. Anyway, these are related, right? So we can measure just one. I hope that was the question. Okay.
Thank you, ma'am.
Then go to the next question. Okay. So this I have discussed in earlier session, in last session. These are the things discussed during the lecture videos also. So I'm giving you this question. So what are the typical, by typical I mean the traditional or conventional methods of breast cancer detection? Okay. You can name a few, we have discussed in earlier sessions also. So what are the typical methods of breast cancer detection? Do not consider it like using biosensors. So this research work is going on in this area. So like using sensors alone, we cannot detect breast cancer or any other type of disease. So I'll take a pause. You can remember it and give me the answer in the chat box.
Yes, mammography.
Mammography, yes. So this is like a X-ray screening technique. And what else? What is the most common one? Not only for breast cancer, generally for any cancer.
MRI.
MRI, yes. MRI is also used for many other purposes. But for particularly cancer detection, biopsy is like the gold standard. So we have studied about this 3 biomarkers. Mammography, yes, that is one option. That is like the screening that needs to be done periodically. Okay, even someone is not there is no tumor, or there is no, like, it's like a regular test that one should go through. uh, so the most common, like the most conventional method is biopsy, where the tissue will be extracted using a needle, and then certain types of biomarkers. So there are three biomarkers for breast cancer, so those are present or not, that will be analyzed. Okay, and we also know that many times even any of these biomarkers are not present, but the still tissue can be cancerous, so the patient may have breast cancer even if it is a triple negative test in biopsy. Okay, so biopsy is most common, then mammography, that is particularly breast cancer. But then we have also studied that it is not useful if for dense tissue. Okay, because it's like x-ray analysis technique. Okay, so if the tissue is very dense, then the x-ray that penetration will not be proper, I guess. So that is why it is not useful for dense tissue. And MRI is also many times, and then like clinical breast exam. So some expert will do that screening and exam, that can also give indication. So these are for like earlier diagnosis. And if some sign is there that the person may have breast cancer, then biopsy is the kind of like the gold standard. Okay. So let me write these things. So one is mammography, MRI, biopsy, clinical. So this is done by some expert examination. So this is CBE. So this is like the initial screening. Okay, and remember, no single method is perfect, and combination of these are used to exactly verify whether the person has breast cancer or not, and in which stage. Next, I will give you a question that is more like an open-ended question. Maybe you can think and give me few answers. There is no definite answer to this question. Okay, uh, give few reasons why biosensor should be, or any sensor in general, should be low cost and disposable. So this is particularly for biosensors. Okay, there is no one certain answer for this. Maybe you can think, we have discussed about so many types of sensors, then what is uh, the reason why biosensors should be low cost and disposable. Maybe you can write in the chat box, if you can unmute and speak also.
Low cost means it should be within the reach of common man.
Yes, it should be affordable to everyone.
And
That is one valid reason. Others want to add something. I think he left the meeting. Maybe there is some connectivity issue. So the main reason is that to allow, I will write it down, safe, first of all, because we are using it for biological sample handling, so safety to the operator is also important, the one that is actually using the sensor. Okay. Safe, hygienic, so that we may maybe we are screening some disease, so we have to maintain a proper hygiene, and that is why we want it to be disposable and affordable. Okay. So the thing is that after using biological sample, it can be like blood, can be tissue, can be saliva, so it is not safe to reuse the sensor. Okay. So reuse can risk contamination, yes, so we want to dispose it properly. Okay, so we don't want to reuse it. It can be a contamination or infection to the other user, infection to the so this is operator also. Okay. And if we want to make a disposable sensor, this is like a single time use, then it should be low cost, right? Otherwise it won't be that cost effective. So people are trying to use like paper or other kind of material, those are low cost, specifically for biosensors. So the materials, those are compatible with biological samples, those are not harmful to biological samples and human being in general. That is like a different study. Okay, if we can make a low cost platform to make biosensors, that can be an advantage. So many people are working in that area as well, not only on the sensor design and fabrication, but the low cost material, cost platform, lab on chip type, uh, those can be useful in bio sensor fabrication. Okay, then only this sensors will come to the market. Okay, otherwise it will stay in the labs also, lab only. Okay. So you may have learned about this, so heard about this term, point of care, POC, point of care diagnosis. So this is like a low cost single use sensor, just to check whether the disease or the biomarker is present or not. It does not give much qualitative information like what is the stage of the disease or how serious the disease is. This just will tell you that okay, there is something, there is some abnormality, there is some irregularity, and you should go for other treatments and other analysis. Okay, other testing. So this term is very popular in this biosensor area, so point of care diagnosis. And this is useful in mass screening, like you remember during COVID we had this disposable kind of rapid antigen test dose kits, right? We cannot make it in that large quantity if it is not low cost. Okay, and it has to be disposable, cannot reuse with other patient. So this is the main reason. You can think of other reasons also. Let's go to the next question. Again, this is a short answer type question. piezoresistive sensors suitable for integration into catheter tip. So remember the piezoresistive sensors that we have discussed, that can be used in catheter for force measurement. So those are MEMS based sensors, right? So like, answer this question remembering that point. Okay, what is the advantage? So these are MEMS sensor. So what are the advantage of using MEMS sensor in this kind of applications? Okay, I actually didn't want to give any option for this, so just let me write down the answer. The piezoresistive sensors that we have discussed, so these are MEMS based sensor. Okay, so they are, first important point is miniaturizable. We can make a very small force sensor. We can make multiple force sensor to attach to the catheter tip, okay, which is already very small. And they offer real time output, like while doing this operation. Okay, we are moving the tip, and it will give, during that movement it will give the force or the output. Okay, and they are compatible with silicon based mass fabrication. Now what is the advantage of that it is be compatible with silicon based mass fabrication? We know that MEMS structures are very small. If we can make it compatible with silicon based MEMS fabrication techniques, which is already well known, already well established, silicon fabrication is well established, right, because of the this boom of electronics. So if we can make anything with that is compatible with silicon based fabrication, the fabrication process becomes very easy in the sense, a lot of the process we already know, like how to coat the photoresist, what kind of photoresist will work, how to make the structure, how to make the mask. These are the things already available, and that actually significantly reduced the cost. Okay, when things are not known, suppose we have to think like what is the chemical to etch certain layer, and we have to think about it and then study about it, then that includes a lot of cost to the overall fabrication process. So we can make silicon based MEMS piezoresistive sensors very easily. We know that we can dope boron in silicon to make a piezoresistive material. We can make electrodes, interdigitated electrodes, and then make a piezoresistive sensor, right? So this allows the overall fabrication process becomes easy, as well as we can go for very small structures because we already know how to make very small structures using silicon, right? So these are some of the advantages. Next question. What are two common applications? So I'm not keeping many MCQ type question into this session because we have already studied a lot about sensors and actuators, so I think you can give answers to these short questions. What are two common applications of FDM printing? Okay, think about it and tell me the answer in the chat box. Which is FDM is what? Fuse deposition modeling, right? So how you do, this is the most common 3D printing technology. We use a thermoplastic filament of ABS or uh, PLA type material, and we heat it, we melt it, and write it using a nozzle. So it's a very basic technique. So what are the main common applications? So let me tell you the answer. So as I mentioned, it allows, suppose we, if we can make uh, our design using material PLA and ABS and other material that is compatible with FDM printing, then we can very easily go for rapid prototyping. Okay, so this is one common example. If we can make some structure using these materials, we can go for this printing rather than going to some other expensive technique. Okay, so this is one application. Next, why it is mostly used in sensors in like fabrication? It is used to make enclosures, coverings, or for say some functional part, some structural support kind of part. Okay, for this kind of we don't want to do like a very use a very high cost thing. We just need some structural support, some enclosure, and we can very easily make it using those plastic. Okay, if I remember correctly, the in the lab video and in the software that was discussed, that can be used for 3D printing, the TA has made one that structure that is like an enclosure. Okay, that is like a covering for the actual device. Okay, in that case it is mostly used. Okay, used to make enclosures and functional and like a structural support okay, can be used in multiple places. Again, let me give you another question on FDM. Why does FDM often require support structure? if you remember, there is like one material that is the actual material for printing, another is the support material filament. Many times we use both. So what is the reason? This is specifically like true in FDM. uh, it is also present in some other types of printing also, but it is mainly required like in the structural support is mainly required in FDM printing. So what is the reason? So, so think about this answer, how the FDM printing is done. Giving you some time, maybe you can find the answer and think about it. So how this in this technique, in FDM technique, the printing is done? So what are the things we should remember about this? What we use? We use a thermoplastic filament, and the writing is done through a heated nozzle. Okay, so these are the material. These are the the system consists of kind of these things. There is this one stage. Uh, there will be XYZ coordinate that you will feed to the system. Okay, to show how to write, and then how basically the process happen, the printing happens, it happens layer by layer. Okay, now say your structure is something like this. I'm just making a random structure. Okay, probably will not use it anywhere, but say you have some this kind of a structure. Now what you will do, it will print, the printer will print layer by layer. Okay, so the structure may not be stable, okay, while writing. So once we tried to write like a bolt, okay, so we didn't have the exact size, so we tried to make this kind of a structure. So this height is very large, and then this is small. Okay, the width. So when you want to make such a kind of a structure, that it, may not be stable when it is writing layer by layer. Okay, one layer as a whole, maybe the structure is stable, but layer by layer it may topple, it may bend, or something like that can happen. And that is why we often use like a support material along with the actual material, and that can be removed later. Okay, that was discussed in the last video, if you remember it. Okay, that is why we mostly use a support material in this printing. We don't need this support material in that laser sintering method. Okay, that material is already in powdered form, so there is no structural support is needed. So the answer is because the writing is layer by layer, an overheating may happen, okay, because we are writing it using a heated nozzle. This is not the main reason. Basically, the structural support is like when you have this kind of a suspended kind of a structure, or where the aspect ratio is very high that it may topple. So in that case, we use the support material. Okay, certain features that depends on the design. Features may fall without an additional support material. So we use a support material. The material should be such that we should be able to remove it easily later stage. Okay, because ultimately that is not a part of the design. Okay, if the our design is kind of complex and it may topple, may fall, in that case we use uh, like a support material. And what is the type of support material that was discussed in the lecture videos, I don't recall it, like I don't remember it right now, but please go through the video and what is the support material that you should know. Okay, what are the material, what kind of material is used for that purpose. Next question is, what is the main limitation of FDM technology compared to SLA, that is stereolithography, or material jetting? I will give you the options here. It is too expensive, B is it uses toxic material, C is it has lower resolution, and visible layer lines, D is it uses thermoplastic. So what is the answer? What is the main limitation? What is the primary limitation of FDM technology compared to SLA, stereolithography, or material jetting? So I'll take a pause. D. So that is what do you think the main limitation? Okay, so if you remember the class, this technique, this FDM technique, this is the least expensive technique. So we can have like this printer does not cost much. Okay, we can buy it for personal use also. The main disadvantage is that here the material flows through this heated nozzle. Okay, so obviously it is limited by the size of this nozzle. So the resolution is poor compared to other techniques. Okay. So in case when you do using a laser or using a UV laser for curing, that will have like a better resolution compared to FDM technique. Another thing is that, as I mentioned, the printing is done layer by layer in FDM. So suppose you want to make like a cube, so it will print one layer of the cube once and then the second and then multiple times. A certain thickness of the material will be deposited on your the surface, like the XYZ stays where you are making the structure. Certain thickness will be deposited, that will be your one layer and then another layer. And I can tell you that you can clearly see all these layers, although ideally you wanted like a completely cubic kind of a structure. You will be still able to see some layers, kind of uneven kind of a surface. Okay, that is because of the layer by layer printing. So this is the main limitation of FDM technology. Okay, it uses thermoplastic, yes, but we are also limited with other material, the in other techniques as well. Okay, for some we need a UV curable polymer, say. In some we need a material that can be sintered using laser, and in material setting we need a material that has like this ink kind of a consistency. Okay, so that we can just inject printing, what is zetting, like spraying, uh, to to have that. We, in that case also, we are limited with material, not only FDM technology. And this is one of the main challenge of 3D printing technology. So this is not the primary limitation, main limitation. The answer is C. It has lower limitation and visible layer lines. You can clearly see the lines, the layer by layer printing one, and many times you don't want that. Okay, so answer is C. Due to nozzle based extrusion, layer lines are prominent in FDM technology. Let's go to the next question. Which 3D printing technique uses liquid resin cured by UV light? Option A is fuse deposition modeling, FDM. We are discussing more about this technique. Stereolithography, SLS, SLA. C is selective laser sintering. SLS. Option D is material zetting. So what uses liquid resin? Which of this technique we have discussed? So what is the answer? We know that it is not FDM, right? There we use a heated nozzle, basically to melt the thermoplastic layer. What happens in SLA? So in this technique we use liquid resin, and to cure it we use UV laser. Okay, so the correct answer is B. In SLS, selective laser sintering, what we'll use a laser again, but in this case we will use a powdered material and we will do sintering. The process sintering means we'll just enough melt it so that it creates like a block, and it when it is solidified, and that's how we will create the structure. And material zetting is like spraying the material, you know, in a certain structure. So the correct answer is B, SLA. Please go through the lab video, the lecture videos, so that you remember little bit about like how these processes are different, so that you remember. Okay. Now the next question is, if you have watched the lecture videos, then you know that so the main materials that we use for FDM printing is ABS and PLA. Okay, PLA is like the more common one. uh, there are certain difference between ABS and PLA, like how the process will be. Now in case of PLA, normally what we do, we use like a heated bed. The platform where the structure will be created, that will be heated, whereas in case of PLA it can be like a normal temperature. Now why this difference comes? Okay, that is the question. It was discussed during the class, that is why I am keeping it as a question. Why is a heated bed typically required when printing with ABS in FDM 3D printing? So what is the reason, if you can recall? So what is the answer? If you can't recall, then let me help you with the answer. So that comes with the inherent difference in the material properties of ABS and PLA. So what happens in case of ABS, it tends to shrink when it is cooled. Okay, uh, that may result in, so if we directly cool it, it may lift and it may detach from the platform. Okay, it will detach from the platform, and the overall the printing will not be exactly the place where we want it for the next layer. Okay, it will shrink, it will detach. Okay, so that is the reason why a heated platform is used. Typical temperature is between 80 to 110 degrees Celsius. It maintains the adhesion, and then it also reduces the stress that is created during the cooling, during printing, and then it gradually cooled so that the structure remain intact. Okay, so these are the reasons. I will write it down. So ABS tends to shrink as it cools, okay, which causes lifting of the layer from the platform or the bed, the stage that is being used. Okay, so usually a heated bed 80 to 110 degrees Celsius, it is used to maintain adhesion. Okay, and the difference with PLA is that PLA usually does not shrink and does not require this. Okay. So I have one last question for this session, so I'll write it. So the question is, complete the sentence. Okay, this type of questions are there in the assignment, so that is why I'm giving. Okay, so dash uses sheets of material which are cut first and glued layer by layer to form 3D structures. So I'll give you three options. Option A is LOM, B is FDM, C is MZ. If you need, I will give you the full form. Maybe I don't know how many of you actually remember these things. So this is material jetting, B, okay, The correct answer is actually A. Let me write down the full form, then you will be able to answer correctly. Okay, material setting. So now you know that it uses sheets of material to cut and glue. So this is not that this is not true. In this case, we like make material like ink kind of material, and then we use UV light to cure this polymer. Okay, this is like inkjet printing, very similar to inkjet printing, not as given in the question. So FDM is fused deposition modeling. That is the basic 3D printing technology that we have learned, that uses some thermoplastic material like PLA and ABS, and it uses heated nozzle. Okay, basically the plastic is melted, and that's how we create the structure. So again, this is not the answer. This is LOM is laminated. So you should remember the full forms. Laminated object manufacturing. So this is LOM, and this is where it uses sheets of material, maybe paper or plastic. These are cut into different like required shapes, and then these are glued layer by layer to create 3D structures. Okay, so that is the correct answer. So answer is A, LOM. So you should remember the full forms of the 5 different 3D printing technology, the basic printing mechanism, whether it is done by layer, whether it requires a support structure or not, how basically the curing is done. Okay, so we know that FDM uses heated nozzle, uh, stereolithography uses UV laser for curing, that requires liquid raising. Okay, and powdered material is required for SLS, selective laser sintering. Okay, these are the things you should remember. I think these will be more than enough for your assignment as well as for exam. Okay, if you are working in 3D printing, then you might need other knowledge of these things also. Okay. So these are the questions that I have today. I don't have any more questions. So if you have any doubt, any question, then you can ask. So this is our last session. I hope that maybe you guys have registered for the exam, and wish you all the best for the exam. And if you have any last doubt, any clarification, then you can ask me. If I can answer here, I will try to answer. If not, then you can post in the discussion forum. I will answer there also. So I hope that the sessions were useful. So I conducted this 12 live session plus one extra session that was like a summary. I hope that the sessions were useful in general learning the topics, and few topics are new to me as well. So I hope that I at least delivered something to you. I'm not sure. Okay. If you want to give any feedback also, you can give. So no question. Okay, then all the best for your exam. Please go through the like a few informations are given here for exams. Maybe you can exam format. Okay, I hope you have already gone through this. Yeah. Yeah, and you still have any question, then you can write in the discussion forum, okay, for your clarification. So if there is no question, then I will stop the session here. Thank you all for attending the session. I hope it was useful, and all the best for your exams. Okay.
Hello.
Yes.
Madam, I have a question regarding what is the how we can decide the thickness of chromium and gold above the insulating layer or above the metal while we are making piezoresistive sensors.
So chromium and gold. So chromium is just used for adhesion. So typically not like few nanometers of chromium. And gold. So we are using it as an electrode, right? So as long as we have good conductivity and ohmic contact, that is enough, right? So for that we see, I don't know, like I never did gold electrode, I never used. But when in my lab they use like for rough purposes they use aluminum electrode, so that is like few nanometer, as long as it gives good contact. So you have to do the deposition and check and measure. Okay, so maybe tens of nanometer or a little bit less than 100 nanometer. Okay, you cannot make very thick gold layer, but for electrodes it should have certain thickness, because if you use probes there will be lot of scratch. Okay, that few nanometer of gold that uh, will get removed. Okay, so it has to have certain thickness so that the probe does not damage it, and there is certain like the contact should be ohmic, right? Ohmic means the IV characteristics should be linear. So you have to check that, and you can simulate it also, like what should be the optimum thickness. If say 50 nanometer thick layer is enough, why would we go for thicker deposition, right? Yeah, so typically in that range around. I don't know about chromium and gold. For aluminum it's around say less than 100 nanometer it works. It should conduct, basically that is the purpose.
Okay, ma'am. Thank you. Your sessions are really useful for us. I attended around 5 sessions out of 12 sessions, and they are useful to go insights into the assignments and go all the video lectures at par with video lectures also. Thank you.
Thank you. I'm glad that it was useful. Okay, so let's stop the session here. All the best for your exams.
Thank you, ma'am.